Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Although the code for sending geometry content to the graphics renderer is ready for use, I would like to spend a bit more time and write an alternate code path for geometry assets which consist of a single LOD with a single submesh. After we finish writing this code, we are gonna go ahead and test the whole thing in this video. We spent the last video implementing a structure that can hold geometry hierarchy information for mesh assets that have multiple LODs and are submeshes. However, when we think of a typical scene in a video game, we can't but notice that most objects shown in that scene are meshes that consist of a single LOD and a single submesh. In other words, each object is one vertex buffer rendered using one material. Although our system can perfectly handle single meshes, it does waste memory because it always allocates at least 16 bytes of memory, and it needs another 8 bytes for a pointer that points to the allocated memory. Realizing that most objects are single meshes, it's not hard to see that our solution is not optimal. And that's why I'm going to check if the geometry that's being loaded consists of a single submesh, and if so, we'll use a different data structure. I'm going to write a function that examines the data to determine if the geometry has only a single submesh. Again, I'm going to use the blob stream reader class and check if the geometry has more than one LOD, in which case we return false. If there's only one LOD in this geometry, then we need to check if it contains more than one submesh. If this function returns true, that means that we don't have to use the geometry hierarchy, and instead we call another function that adds a single submesh to the renderer. Since we know that we only have one LOD and one submesh, we can easily skip everything else to get to the submesh data and call graphics add submesh to send the data to the GPU. Now the only piece of information that we need to save is the ID that's returned to us by the graphics renderer when we add a new submesh. Remember that for multiple submeshes, we have a list of GPU IDs in the geometry hierarchy, whereas now we only have got one ID. Instead of putting that in a separate list, we can use the same free list that contains pointers to geometry hierarchies. And the way I'm going to do that is by marking the items in the list if they don't represent a pointer, but contain an ID instead. To mark a pointer, we make use of the fact that malloc allocates memory at a location that is aligned as the fundamental alignment of the platform. The fundamental alignment for 64-bit platforms is 16 bytes. This means that a pointer that's returned by malloc always has a value that's a multiple of 16. If you look at the binary representation of a number that's a multiple of powers of 2, we see that the least significant bits are always 0. Depending on what the alignment is. For example, for any number that's a multiple of 2, only the least significant bit is always 0. Numbers that are multiples of 4 have their 2 least significant bits zeroed. First 3 bits for multiples of 8, and so on. We can easily recognize a pattern here. The pattern being that the number of least significant bits that are always 0 is the same as the value of the power of alignment. So for a 16-byte alignment, the 4 least significant bits are always 0 because 16 is 2 to the power of 4. That means that we are free to use these 4 bits to mark an item as not being a pointer. So I'll create a fake pointer here that has its least significant bit set, and then I put the GPU ID in the most significant bits. Obviously, we need to make sure that the pointer size is larger than the size of the ID type. Then we calculate by how many bits the ID should be shifted to the left. Next, we shift the GPU ID by this number of bits to the left, and I'll also define a single mesh marker constant, which is used to just set the least significant bit of the fake pointer. We do this by logically ORing the values. Now that we have a fake pointer, we can lock the free list and add it to the hierarchies. I'm also going to assert that even if you target some other platform that's not 64-bit, we still have at least 1 bit in the pointers that is always 0. Also note that we could put these static asserts anywhere in the engine, but for now I just put them here where they make the most sense. When we want to unload a geometry, we need to check if it's a real pointer or one that contains an ID. We can do this easily by checking if the single mesh marker bit is set or not. If the pointer contains an ID, I'll call a function that gets the ID from the fake pointer. This is pretty much the reverse of what we did earlier. We shift the ID by the number of bits to the right. We still need to call the low-level functions in the renderer to add and remove submeshes. Let me also update the comments here to describe the output format for multi-mesh and single-mesh geometries. In theory, we should be ready to upload geometry content to the GPU. However, we never tested the upload context to see if it actually works. So let me quickly write a test in our test application to spawn a couple of threads, which will then try and create GPU-only buffer resources all at the same time. Here we see the application running, and when I exit the application, we can still see some GPU activity, and that's due to OBS, which is the software I'm using to record this video. Now, instead of writing a specific test for multi-threaded buffer creation, I'm going to write a generic function that spawns a number of threads and lets them run any worker function that we provide. I also make it possible to turn it on and off using a macro definition. The number of threads is 8, but you can choose any number, of course. We need a Boolean variable to let the worker function know when to exit, and we define an array of threads that will run a worker function. The generic thread initialization function will take a function and its parameters, if any, and passes them to a new thread which will run immediately. When we want the thread to terminate, we set shutdown to true and wait for each thread to join. Now we can write a test worker function for testing the upload context. First, let's have a buffer that we can upload. It doesn't matter if it contains any data because we are not using it in any way, so it might as well be filled with zeros. I allocate a buffer that has a size of 1 megabyte. I won't test for other sizes for the sake of time, but I would recommend doing so for both larger and smaller sizes to make sure that we didn't miss any edge cases. Now for the test worker, I need to include an API-specific header for the low-level renderer. The test application is intended to test the high-level functions of the engine, which are API and platform independent. But I'll add this temporarily just to quickly test the upload context. While this thread is running, we keep calling createBuffer function, which will upload our buffer to the GPU. Remember that 8 threads will be doing this at the same time. After each upload, we release the resulting resource, which will remove it from GPU's memory. We don't have to use deferred release here, because the buffer is not used anywhere for rendering. But it will be a good test for the deferred release functionality. During the initialization of the application, we can call this function to spawn the threads, and when we shut down, we wait for the threads to exit. When I run the application, you can see that the copy engine is being used, which means that our buffer is being uploaded to the GPU. We can also see the messages in the output panel about upload buffers being created with the same size as our fake buffer. When I set a breakpoint at a point where we have to wait for an upload frame to become available, we see that it's hit, which makes sense because we have 8 threads trying to upload, where we only have 4 upload frames. Another place where we can put a breakpoint is where we wait for the GPU to execute copy commands. It's also hit, which means that the GPU is really doing something that takes time. Of course, none of this is a conclusive proof that our system is 100% correct, but it appears to be working fine at the first glance. When I close the application, we see that the copy engine is no longer being used. By the way, some GPUs don't have a copy engine, even though the task manager shows one. In that case, you won't see any activity for the copy engine. The 3D engine, however, should show a higher utilization. Last but not least, I check if we have any live objects, which is not the case. So our test was a success, and we are now finally ready to upload one of our imported geometry assets to the GPU. Before doing so, let me add the concept of primitive topology to the editor side, because we didn't have that yet, but we'll need it when we pack geometry data for the engine. I'll add a new property for primitive topology in the mesh class. When reading the imported data that come from content tools, we set primitive topology to triangle list. That's because content tools currently only support triangle meshes, which will be imported using an index triangle list format. When we load a geometry asset file, we read this new property, and when we save a geometry asset, we need to also write the primitive topology type for each mesh to the asset file. In order to pack data to be sent to the engine, I'm going to add a new abstract method to the asset base class. This is because this method is going to be needed for packing data for other asset types as well. So here we need a method that packs the asset data in a specific format and returns an array of bytes which we can send to the engine. For the implementation of this method, we need to pack the data in the same format that's required by the engine. Fortunately, our geometry assets are already pretty much in the correct format, so all we need to do is to copy some data and align a couple of buffers as needed by the engine. We can simply copy and paste the format description from our C++ code. We can use a binary writer to write the geometry data in this format. First, we fill in the LOD count, and then for each LOD, we fill in the threshold value and the number of submeshes. Because we don't know what the total size of submesh data in this LOD will be, we remember the right position of the binary writer so that we can come back and fill it in later. For now, we write a 0 just to reserve some space for it in the buffer. Next, for each submesh in this LOD, we'll write the element size, vertex count, index count, elements type, and the primitive topology. Final pieces of information that we need to pack are the vertex and index buffers. However, we need to align the position and element buffer sizes to be a multiple of 4 bytes. To do that, I can just copy the alignment functions that we wrote in the previous episode. They can't be generic functions because C# generics are different from C++ templates, so we give the alignment values as one of the function parameters. Of course, the essence of both functions remains the same. We can allocate new buffers with properly aligned sizes and copy the vertex data into these buffers. So I'll make a buffer for vertex positions and another one for other vertex elements. Now we can write these new buffers to the output stream. The index buffer can be used as is because it doesn't need any alignment. The last thing that remains is to go back and fill in the total size of submeshes in this LOD. We can calculate this value by subtracting the start position of submesh data from the current stream position. Note that we subtract the extra 4 bytes to account for the bytes that hold size of submeshes. Then we go back and write this value into the stream and reset the current write position. After we are done writing all geometry data to the stream, we can put it in a byte array and return it. I messed up the scopes here, so let me fix it first. As you can see, we can run the test application and also the editor. Because we added primitive topology to our meshes, we need to re-import these models in order to be able to use them. So I'm going to delete these files and drop the FBX files onto the content browser to import them. Here we see our models again. There is also this new model, which I'm going to use to test our upload code. This model has a single LOD with 5 submeshes, and you can find a link in the video description where you can download it from my Patreon page if you're a patron. If you're not and you like these videos and want to see more of them, then please consider supporting this channel on Patreon, which will help me spend more time working on these videos and developing the game engine. Of course, you will also get access to the engine's codebase and you will be able to download all game assets that I use in the videos. Because we are not using the renderer here in the editor, we can't directly send this byte array to the engine. What we can do is to save it to a file, then load it in the test application, and there we can send it to the engine. So I'll add a temporary block of code here that will save the byte array to a file in the engine test location. And we are going to call this method whenever we load a geometry asset in the editor. As you can see, opening this model now creates a file in engine test project folder. We can open any of these files, of course, but I'm going to use this new model. I'll comment out the call to the packing method because we don't want to save a file every time we inspect one of those models. In the test application, we need a function that reads an entire file into memory. We already have a function for that, and since it's test code, we are going to duplicate the function and use it here. This function is located in contentloader.cpp, which still isn't a great place to have it, but maybe someday when we have a file IO header, we can move it in there. In order to use this function, we need to include the file system header. I also turned off the multithreading test functions. And we need to include fstream header for file operations. Then we can try to read the model file that we just saved. If we want to create a resource in the engine, we need to include content to engine header. We are also going to remember the resource ID so that we can remove it when the application is closed. Finally, we call createResource to upload the geometry and destroyResource to remove it from the engine. I'm going to step through the code and see if everything works as intended. We can see right away that we have one LOD and 5 submeshes for this model, which is correct. Therefore, this function returns false and we are going to create a mesh hierarchy instead. The size of geometry hierarchy buffer is 32, which also looks right. We can inspect the data that we are filling in. The threshold is -1, and that's right because we have a single LOD. The offset also checks out. Next, we step into low-level renderers at submesh function and check if there is anything out of order. For example, we can see here that the elements type has a value of 3, which, if we look at the elements type enumeration, corresponds to a static mesh that has normal and UV information. And this is indeed what I'd expect with this particular model. We can also see that buffer resources are being created with a size that is the same as the total buffer size that we calculated here. In total, there are 5 buffers created, 1 for each submesh. And when we close the application, we can see that the hierarchy pointer is indeed not marked, and therefore we need to use the geometry hierarchy stream to remove submeshes one by one. I didn't test a single mesh code path for the sake of time, which is not the greatest idea, but then again, if it doesn't work, we'll find out soon enough. This is it pretty much, and as a final check, we'll have a look at the output panel to make sure that we didn't leak any memory or have any live objects left. Great. This concludes uploading geometry content to the GPU, which also lays the groundwork for uploading other asset types, such as textures or even raw data, to be used for rendering. Thank you so much for joining me today, and I hope to see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!